Good morning to all of you. I welcomes to all in our quantum mechanics series. And in our last class we have been discussed about eigenvalue and eigenfunctions and eigenvalues. And each and every steps we have been discussed in our last class. And this is nothing but the so-called the eigenvalue equation. This is eigenvalue equation. This is the observable operator. This is the eigen function and this is eigenvalue. This is psi q is nothing but eigen function of operator q cap and this is its corresponding eigenvalue. Today we are going to discuss about eigenvalues and eigenfunctions of Hermitian operators. So the above topic, that means this topic is discussed by two theorems, that we are going to be discussed by two theorems. So let's start. Eigenvalues of Hermitian operator are real. Theorem 1, we have to prove that eigenvalues of Hermitian operators are real. Whenever we have been discussed about Hermitian operator, at that time I have been told to you that the two conditions or the two relations should have to be a Hermitian operator has to be obey, that is the average mean value of a observable quantity will be equal to its complex conjugate. That means the Hermitian operator has to be a real eigenvalue that we are going to be prove. That means here the expectation value of q or a observable value or a physical observable is equal to its complex conjugate. So any measurable quantify the expectation value must be real, that we have been at that time we have been discussed, and also this condition should have to be obeyed by a Hermitian operator. So by considering this condition we are going to be prove that eigenvalues of Hermitian operators are real. So let q cap be a Hermitian operator and psi n be an eigenfunction of q cap belonging to the eigenvalue is qn. Hence the corresponding eigenvalue equation whatever we have been discussed in our last class will be q cap psi n will be equal to small qn psi n. Let this is equation number 1. Now we have to multiply psi n star both the side of this equation number 1 and integrate over entire space. Here it is written as 1d. In bracket I have been written 1d. Entire space we obtain integration over psi n star. I am going to multiply this psi n star with this equation number 1 and integrating psi n star q cap psi n dx. Here qn is a constant, I have to take outside the integration qn integration over psi n star psi n dx. Let this is equation number 2. So here one thing I want to say that we are considering the one dimensional dynamics of the particle or one dimensional system, 1d, that is dx. Here integrating along dx means along x axis the dynamics is happens in our case whatever we are considering, this is one dimension along x axis, okay. But you can consider also 3D format of this equation. It will be psi n star q cap psi n dqr and dqr 3D format. Not to be for this derivation, if you are going to be you are going to be asked in your exam, you can write in either way. Either you have to write in 3D format or either you can write in 2D format. But here in our discussion, I am considering the 1D format. Okay. So since q cap, this box, this 3D, this red color things should not be write in your exam. Okay. So if you are writing in 3D format, then you have to write all the terms are 3D. Okay. dqr, it will be here. You have to write dqr like that. Since we know, since we have been accepted q cap is a Hermitian, then this equation can be written as psi n star q cap psi n dx will be equal to, as this is Hermitian, then it will be q cap psi n whole star psi n dx is equal to, suppose here from the Eigenvalue equation, q cap psi n equal to qn psi n. If I am going to take the star, whole star, it will be qn star. So it is qn star psi n dx. Another thing I want to share with you, this sentence it is written that multiplying psi n star both the side of equation number 1 and integrate over entire space. Okay, here entire space I have been not considered anything limit. Here I am not consider any limit. This is open for you, that if the dynamics is from infinite to infinite, then I have to write, we have to write minus infinity to plus infinity. If a dynamics is happens in between 0 to L, I have to write integrate over 0 to L. If it is minus L to L, minus L to L, we have to write. So this limit has been opened here, that we have to consider the particular situation where the particle is in dynamics. That limit we have to be put. So only for that I have been in generalized, I have been opened this limit. Okay. So integration over this will be studied as integration over entire space. Integration over entire space, this equal to this equal to this. Now integration of over entire space, psi n star q cap psi n dx is equal to qn star integration over entire space psi n star psi n dx. Let this is equation number 3. Now we have to subtract equation number 2 and 3. Okay, this is the equation number 2 and this is the equation number 2, 3. If we are going to subtract 3 from equation number 2, or you can consider also subtracting 2 by 3, at last you are going to get the same answer. Here I am subtracting equation number 3 from equation number 2. So I have to be right in that way, it will be better for you. So now subtracting equation number 3 from equation 2, from equation number 2, we found that, see, this side, this left hand side is same with this left hand side. So it will be subtracted and you are going to get 0. This right hand side will be qn minus qn star, and integration over this one is equal to 0. Okay, since this one will be not equal to 0, because or this psi n star psi n will be also psi n mod square dx. It is indicating one type of probability density, or you can say psi n is a square integrable. It is a square integrable means it will give you one value. Psi n square dx is a square integrable means it is representing the density, probability density. So it will be has a value, could not be 0. So psi psi qn minus qn star will be equal to 0 or qn equal to qn star. That means a value and its complex conjugate both are equal. That means eigenvalue is a number, eigenvalue is a value only. Okay, dimensional less value. It will be a dimensional less value. Qn will be equal to its own complex conjugate. That means it has to be real. Okay, so eigenvalue of Hermitian operator is real, hence it has been proved. Now we have to consider another theorem is this one, that any two eigenfunctions of a Hermitian operator belonging to different eigenvalues are orthogonal. This is the theorem that we have to prove. Actually what it is, that any two eigenfunctions, suppose let that two eigenfunctions is psi n and psi m, be two eigenfunctions of a Hermitian operator q cap. For this Hermitian operator, these are the two eigenfunctions, suppose, belonging to eigenvalues qn and qm respectively. The two eigenvalue equations are, so if it is so, suppose for this operator these are the two eigenfunctions and having the different eigenvalues qn and qm, then this this psi n and psi m both are orthogonal with each other. In short, I can say to you, the so called orthogonal means is like this. Suppose x axis and this is y axis, the vector is I cap j cap. Orthogonal means I cap dot j cap will be equal to 0. That means both are perpendicular with each other. That means the dot productivity between the both component will be not there, will be equal to 0. What is the dot productivity? We can say, suppose a dot b, that means a cos theta or ab cos theta. Suppose this is ab cos theta. That means suppose this is, I can say to you that this is a vector and this is b vector and this is theta. Okay, so here a dot b means a magnitude into b magnitude into cos theta. What do you mean by b cos theta? B cos theta means the component of b along a. That is called as the b cos theta. But here, if the two vectors are orthogonal with each other, they are not, or one vector don't have any component along this direction, or this vector has no component along this vector, along this side. So we can say that these two vectors are linearly independent with each other. So the physicality, whatever we are going to be discussed for this theorem, that I am going to be explain. Whatever I given one story in this way, or with this story I am going to explain. You just wait. I have to discuss the mathematical things. So this is the so-called orthogonal, that we have to prove that the dot productivity of the two wave functions psi n and psi m will be equal to 0. That we have to prove mathematical. Then I have to discuss that corresponding philosophy or story, whatever I have been considered in your last class. So multiplying psi n now. So here, if it is so, then the two eigenvalue equations are what? Q cap psi n will be qn psi n, q cap psi m will be qm psi m. Multiplying psi m star with equation number 1, and integrate over entire space, we can get psi m star q cap psi n dx is equal to qn, because q cap psi n will be equal to qn psi n, though qn can be taken as outside. This is nothing, this mark is nothing. Actually this is a mark is nothing. Okay, so only this is plain qn integration over psi m star psi n dx. Let it is equation number 3. Since q is Hermitian, then it will be this can be written as q cap psi m star psi n dx. Here q cap psi m will be qm, as it is complex conjugate, so we can write qm star psi m star psi n dx. So qm star integration over psi m star psi n dx, let it is equation number 1. Now from from theorem 1 we found that qm star will be equal to qm, or eigenvalue of a corresponding wave function will be real and its complex conjugate will be itself. So instead of qm star we can write qm. So now the equation number 4 will be qm star q cap psi n dx. This will be equal to, instead of qm star I can write qm integration of over psi m star psi n dx, equation number 5. Subtracting equation number 3 and 4. Subtracting equation number 3 and 4. This also I have to modify somewhat. Subtracting equation number 4 from 3, it will be better. So 3 is what? Where? This is the 3 equation. Equation number 3. Okay. Equation number 3 is this one. 4. The equation number, sorry, here. Subtracting equation number, this is equation number 5. Equation number 5. Subtracting equation number 5 from equation number 3. What we are going to get? We are going to get, see, this is qn, qm. So qn minus qm psi m star psi n dx, and left hand side will be same, will be equal to 0. Since qn and qm are two different values of two different wave functions, so that qn minus qm not to be equal to be 0. It could not be equal to be 0. Then it follows that this will be equal to 0. This will be equal to 0. This is equation number 6. And here am is not equal to n. Am is not equal to n. So this is the proof of psi m and psi n are orthogonal. See, this is one, you can consider this is one vector, this is another vector, and both product will be equal to 0. That means they are orthogonal with each other. And this equation number 6 also called as orthogonal condition. Orthogonal condition. Okay. So here I can give one example that yesterday or in our last class we have been taken one example that if the eigenvalue, suppose psi q, so suppose this person, these are the three official staffs, and both have all have different eigen or different wave functions, and means different wave functions means they can give the different probabilities to finding your brother's position. But if we are going to consider the eigenfunction, that is one function from which we are going to extract the same answer, that is x equal to 2. That will be called as psi q, eigenfunction of these three persons. Now suppose this situation, suppose another three staffs are sitting at another places. Suppose these are the three staffs sitting at one place, and these are the persons who are sitting at another place. So these persons eigenfunction is psi q. Okay. So whenever psi q, or here we have been considered psi n. Okay, psi n. Suppose these persons staffs have eigenfunctions is psi n, which gives the answer of your brother position is x is equal to 2. Okay. Suppose these three persons, they have eigenfunction is psi m. So whenever I have to apply the operator that where is my brother is operator, or you can say a position operator. Whenever you are going to apply, these three has been told to you that your brother is not inside the college. That means the brother is gone away, the class is over and brother is gone away. See, the one college, three staffs is telling that your brother is in lab, and another three staff, the same college but other office, they are telling that brother is not inside the not inside the college, means this psi n and psi m, there is no connectivity. Some group is telling that brother is inside the college, some groups are telling that brother is not inside the college. That means they are both very different, or we can say they are linearly independent, there is no dependency. So, or we can say the dot productivity of the two waves, the two vectors, will be equal to 0. That means one's component is not having other, or means along A there is no component of B, or along B there is no component of F of A. Or we can say the so called mutual orthogonal with each other. So if two functions psi n and psi m have two different eigenvalues, then both the two eigenfunctions are to be called as orthogonal with each other. Okay. So this is the orthogonal condition that you have to remember. This will be called asked as 1 mark always in your exam. Now orthonormality condition. It is always known that eigenfunctions of a Hermitian operators are square integrable. Okay, we know that it is obvious. It is very true. So they must be normalized to be unit. That means psi n star psi n dx will be equal to 0, or psi n mod square will be equal to 0. Let it is equation number 1. Or we can say, or this can be written as psi m star psi n dx will be equal to 0 for the condition if m equal to n. Let this equation number is 2. Combining equation number 2 with orthogonality condition. See, this equation is psi m star psi n dx is equal to 1 for m equal to n. Here psi m star psi n dx equal to 0 for m not equal to n. So if I am going to combine this equation, that is orthogonal condition, and this equation, combining these two equations, we can write psi m star psi n dx will be equal to Kronecker delta mn. Kronecker delta function is nothing but, this delta mn is nothing but, will be equal to 1 when m equal to n, will be equal to 0 will be m not equal to n. So this overally or in generalized, we can represent both orthonormal and orthogonal condition in one equation, which is called as the orthonormality condition. That is psi m star psi n dx equal to delta mn, which will be equal to 1 when m equal to n, equal to 0 when m not equal to n. So this is the generalized equation which is called as the orthonormality condition. Okay, so 3 conditions that ortho like maybe you will be confused that ortho, one is normalization condition. Normalization condition you have been studied. Orthonormality condition, normality, or orthogonal. So 3 conditions you have been studied, and you have to conformly you have to remember. This is orthonormality condition and this is orthogonal condition. Orthogonal means both are linearly independent and it will be 0, and orthogonal means that is 0. Orthonormal means will be equal to a Kronecker delta del mn. So this is the notes and discussions for today's class. You go through this video and you can write the notes from this video. Whenever you want, you can pause and you can write. So thank you so much for watching this video. Thank you.